One of the neatest things about truly exploring history is how it can change and adjust your perspective on events and things you thought you knew a bunch about. This is a story of disruption, of brilliance, of the power that the right approach can have when solving a problem, especially one involving race cars. The story may not have villains and heroes in the traditional sense, but it does take on a larger dimension when one takes into account the time and place it's set in, the traditions that were challenged, and the norms that were busted. This is the story of a little engine, an engine designed to dominate. The Ford dual overhead cam 255 cubic inch Indy V8, and it's a story that starts back in 1962 with pushrods. I'd like to mention the primary source materials I used in the making of this video. There are a handful of Hot Rod Magazine stories from 1963 and 64, Leo Levine's incredible book Ford, The Dust and the Glory of Racing History. Then there was the Design and Tuning of Competition Engines by Philip Smith, and finally the 1964 Society of Automotive Engineers report filed by Ford's A.J. Scussel entitled The Ford Dual Overhead Cam Competition Engine, along with numerous newspaper stories along the way. So, now that we have that cleared up, here we go. While the Indy 500 has had some of the most wildly weird and innovative American race cars ever built among the list of machines that have attempted to master the speedway and its grueling pace, researching this story opened my eyes to one very specific thing. In some ways, it was also the least creative race in the world. By the time 1962 rolled around and our story starts, the Meyer-Drake Offenhauser engine, an engine designed in the 1920s and still stands as a soaring example of race engine design, had won every Indianapolis 500 since 1947. Not only that, from 1950 through 1962, 13 runnings of the race, including, of course, the 50 and 62 runnings, of the 429 available qualifying spots, meaning 33 cars for 13 years, 416 of the 429 had been filled by Offenhauser-powered cars. There was the occasional Novi, a Cummins diesel on the pole at the 1952 race, and even a Ferrari in 1952, but this was an Offenhauser race. It was also a roadster race. Yes, there were amazingly talented builders, and the cars were all one-off and tailored to their own ways to the builders and drivers, but the basic design of an Indy Roadster, outside of a couple of stark examples, was very, very close all along the board. Now, long story short, the Indy 500 had become a race with a rulebook wide open enough that it was ripe for the picking, but it had a participant base that had become some of the most monkey-see, monkey-do in history. For many people, it was an American race for American engines and American cars with American drivers. And sure, there may have been other ways to do the job, but this was our way, the Indy way. And it would go that way until somebody forced it to change, but who knew that somebody would be a lanky kid from New York named Dan Gurney, a guy who got Ford's ear in the early 1960s. In 1961, the legendary driver Gurney was just a kid, and he saw Jack Brabham show up at the Indianapolis 500 with a little Cooper chassis race car powered by a puny Coventry Climax engine. The establishment just about laughed him out of the joint. That was until the very first car to show up at the Indy 500 after World War II with its engine behind the driver finished ninth with its tiny little engine and the ability to basically run the track at full throttle every lap. Dan Gurney knew what the future was, and the rising racing star needed to figure out a way to get to the speedway and do it in a car like that. In early 1962, Gurney won the Daytona Continental Race, which is the forerunner to the 24 Hours of Daytona. Because of that triumph, he met a few Ford racing people, made a highly positive impression, and continued winning races on a global scale. Now, at that time, he was a factory works driver for the Porsche team. Now, it didn't take long, especially with his performances in sports cars and the Porsche F1 effort, for Gurney to get scooped up for an IndyCar ride. And that call came from Mickey Thompson. Gurney drove a car designed by John Crosswaite. It was tube chassis, it had the engine behind the driver, and that engine was a Buick V8. With the displacement rules at the Indy 500, Thompson believed that the Buick engine would be a good fit for the application. Now, weirdly, he was close to being right. Gurney qualified the car in the 8th spot and was a top 10 runner all day, and that wasn't until a mechanical failure in the transmission parked him early, thus ending his first Indy 500 experience. But there was somebody with him more important than even Mickey Thompson, and that was a man named Colin Chapman. While competing against Chapman's Lotus Grand Prix cars in Europe, Gurney had struck up a friendship and a respect for the opinionated, sometimes arrogant, forward-thinking designer of lightweight, simple cars that were fast as blazes. Colin Chapman had no real interest in the Indy 500. As an Englishman, it just didn't mean that much to him. Gurney, though, had a lifelong knack for finding the right people to partner with in the racing world, and he actually offered to pay Chapman's freight to come over just to watch the race and observe. Colin Chapman was enthralled. In fact, the evening following the race, while both men were on a plane flying from Indianapolis to Monaco for the Grand Prix, Chapman could talk about nothing else, and he saw exactly the path that needed to be taken to win the Indianapolis 500, and he had the same ideas as Dan Gurney. Now, there was another guy walking around the Speedway in the waning days of the month before the race as well in 1962. I'm not sure how many people could have picked Don Fry out of a crowd, but as the general manager of the Ford division of the Ford Motor Company, he wielded a level of power few people could comprehend. Walking through the garages and then the grid, he saw a fleet of cars that were powered by Offenhausers and, of course, a single Buick. Beyond that, he saw opportunity. He knew Ford needed to get involved in championship car racing as it was known at the time, and specifically with the Indy 500. On that 1962 grid, Fry ran into Hot Rod Magazine's Ray Brock. Brock was one of the most influential automotive journalists of his time, and he had a knack for getting his way into factory stories. He was an engineering-brained guy, he was respected by those engineers, and he got a lot of great scoops about engines and forward-looking factory race projects. In the course of what was likely a short conversation on that grid, Brock asked Fry a question about Ford getting involved in the race, and Fry came back and said, quote, "Next year we plan to race one and maybe more cars here." Now, Brock wasn't sure if he was kidding or not, but then again, no one else at Ford knew this either. Returning to Dearborn, Fry began a campaign to get engineers and other senior executives on board with his effort. By July, he had booked a rather secretive meeting with both Colin Chapman and Dan Gurney. In front of a skeptical group of engineers and executives, Chapman laid out a plan with a level of self-assuredness only he could deliver. The engineers are skeptical and some outright dismissive of the idea, but sometimes in life, the obvious things, after something has been done a particular way for so long, are almost impossible to actually grasp, even by the smartest guys in the room. Chapman's idea was as simple as the day is long. Ford needed a very light car with a very light engine, making about 350 horsepower. This would give that team the ability to make less stops for tires and fuel than anyone else, and in theory, the race would be a cakewalk. Beyond that, the rudimentary, high-riding, heavy roadsters of the era were seen by Chapman as sitting ducks. These things were basically tractors in his eyes. Not only could Ford win, with their Lotus chassis and their own power plant, they could trounce everyone. Among the men in that meeting was a man named Bill Gay. He was Ford's executive engineer for the advanced engine section of the company. After listening to Chapman, Gay decided to go out and see for himself if what this British guy was saying had any truth to it. Bill went to some races following the Indy 500 and saw exactly what Chapman did. The Indy 500 in championship car racing, as it was known at that point, was suffering from engineering rigor mortis. It was a revelation for him, someone who had never actually studied the scene. After seeing what he saw at the races he visited, Bill Gay bought all in on this project, and when that happened, the resources of the Ford Motor Company were freed up and the project began in earnest. Principal design engineer Joe McCura was recruited for the job, as was design engineer Richard Chen. Chen's work would be concentrated on managing the weight of the engine that the company would develop. Now, Colin Chapman's company, Lotus, would be responsible for the design and construction of the chassis. Ford would handle the power. But that raises a question. Where to begin? As it turns out, the foundation of their answer was already right in front of him. The Ford 221 cubic inch V8 was the smallest, lightest, and most compact engine of its type in the early 1960s. It made about 150-some horsepower in the Fairlane, and a hotter version of it was brought out to 260 cubic inches and produced 260 horsepower in the early versions of the AC Cobra sports car. Because the Ford company was shooting for a 255 cubic inch displacement for the race engine, this was the natural place to begin investigating. And by August of 1962, Ford engineers had developed their goals and objectives for the Indy engine. They were as follows: a 350-pound maximum weight, 325 reliable and usable horsepower, It would be powered by gasoline, not methanol, for fuel economy. It would use carburetors, not fuel injection. It would be tested and refined in phases, only advancing to the next phase when the previous one was complete, and the final phase was race day in late May of 1962 at the Indianapolis Motor Speedway. Phase 0 was the absolute starting point. It was going over a stock version of the 260 horsepower, 260 cubic inch Cobra engine. Phase 1 had a deadline of September 1st, 1962. It was to determine what the maximum horsepower output would be with a pushrod version of the engine and to benchmark it against the output of the Offenhauser at the time. If the numbers lined up, they'd move to Phase 2. But this went far beyond a simple engine build. Ford bought an Offenhauser and had it properly tuned by an experienced Offenhauser racer. They ran it on methanol on their dyno, and the engine produced 378 horsepower at 6,000 RPM at first, and output was eventually capped at 401 horsepower when all the fine-tuning was done. Next up, Ford surveyed Indy 500 winning drivers to understand the best methods of driving the racetrack in the fastest way possible. They got with the likes of Roger Ward and others for this task and to get the information they wanted. They then made a deal with A.J. Watson, the famed chassis builder, who allowed them to study his chassis, which was used to then estimate the loads placed on a car at speed, how the roadsters worked, and what their strengths and weaknesses were. The capper of this whole process was conducting an incredibly detailed survey of the actual racetrack itself. By the time they were done, they knew where every bump, nook, cranny, and undulation was on the surface and exactly how it should be negotiated. Now, during the summer of 1962, working with Watson, Ford rented the Indianapolis Motor Speedway and had Offie-powered roadsters, or at least one of them, making laps. They were studying the cars for their trap speed on the straightaways. Now, what they learned was that the Offenhauser engines, which used a high-torque camshaft option, and this was a camshaft that used 250 to 270 degrees of duration, were actually faster than those equipped with larger, more aggressive camshafts aimed at peak horsepower. The cars equipped with the higher torque-making camshafts drove off the corners harder. Now, they generated slower trap speeds on the straights, but overall quicker lap times because of that off-corner acceleration. The engineers immediately knew that horsepower was a factor, but maximizing torque was a primary goal. As all this was happening, the engineers were working around the clock inside of Ford to meet deadline number 1. The September 1st internal Ford report suggested advancing the project to Phase 2, which meant creating the first version of an all-aluminum Ford 255 cubic inch V8. While the first sets of blocks and heads were not perfect, they did serve as a perfect test mule for the dyno thrashing portion of this program. With its iron sleeves installed, the block weighed 72 pounds. The cylinder head castings weighed 16 pounds apiece. Now, at this point, I want to stop and talk specifically about the engine in question here before we advance our timeline in the story, as this thing is just a mean little piece and a very, very cool part of the engineering history of the Ford Motor Company and its racing action. Remember, these guys were basically making an all-out racing version of a family car engine. One that had already been braced up to make 260 horsepower in a sports car was now going to be asked to make nearly 100 more horsepower by optimizing every inch of its little self. The aluminum block varied from the factory iron piece in a few significant ways. For starters, the bore, via the iron liner set into it, was shrunk from 3.8 to 3.76 inches. By shrinking the bore, the factory stroke of 2.87 inches could be used and 255 cubic inches would be achieved. Main caps 1 through 4 were now 4-bolt style as opposed to the 2-bolt mains in a factory layout. 2 additional head studs are added to each cylinder to allow for more clamping force when the heads were bolted down. Now, the actual deck of the block was made thicker as well, measuring 640 thousandths of an inch. The diameter of the head stud bosses was doubled for increased clamping force as well. All the plugs in the block were changed from the cup-style tap-in type to screw-in style pipe plugs so they could not come out. The engine would use a dry sump oiling system, use a magnesium oil pan, and all the various pumps and accessories would be gear-driven under a magnesium front cover. The distributor was also gear-driven and moved from its factory location due to packaging constraints and a tight little racing chassis. The crankshaft was forged of 4340 steel alloy and, as mentioned, had a stroke of 2.87 inches. The journals were the same size as the factory Fairlane unit, and the crank was cross-drilled for oiling. Stock-style Clevite bearings were actually used inside the race engine, incredibly. The aluminum heads had slightly enlarged combustion chambers to fit a 1.8-inch intake valve and a 1.5-inch exhaust valve. Now, they were cast using experimental patterns once considered for a high-performance version of the Fairlane engine from the factory. The pistons were forged aluminum with 12.5-to-1 compression, and the engine used stock factory-forged connecting rods of the high-performance 289 style. Now, they did slightly beef up the cap for a larger rod bolt, which these rods had also been shot-peened, magnafluxed, and polished, but otherwise, they were pretty much stock rods. Now, they're also opened up on the small end to accommodate a bronze bushing and a floating-style wrist pin. The pistons themselves used the very common 3-piston ring style design at the top, and the camshaft tunnel bore was actually increased a little to allow for a larger diameter cam, promoting strength. The cam specs were 510 lift, 340 degrees of duration, and 124 degrees of valve overlap. Now, dual valve springs, hollow valves on the intake, and sodium-filled valves on the exhaust were used and retained with lightweight materials due to the high RPM nature of the engine. The pushrods were of a hollow tube design. Now, the intake and exhaust ports were redesigned and contoured to promote airflow across the valve, and initially 4 46mm dual-throat Weber carburetors were used on the engine. The rocker studs in the cylinder heads were increased in size to 0.7 of an inch, and initially cast-iron factory-style rockers were used with jam nuts, Loctite, and then roll pin retainers on the studs themselves to make sure they didn't pull out of the heads. Oiling the valve train was not done by shooting oil up the pushrods, but rather had its own dedicated tube for increased volume and control. The engine used an Autolite breakerless ignition system, Autolite spark plugs, and the timing was maxed out at 43 degrees at a screaming 7,000 RPM. A Varley battery and Mercury Marine generator were used for the power side, and the engine's water pump was gear-driven, just like all the rest of the systems. By the Phase 2 deadline of November 1st, 1962, factory engineers had a running engine on their hands, and durability testing was set to begin. With one catch: the carburetors. After working the math over, Bill Gay and his crew knew that the 46mm Webers were actually going to be costing them some power and potentially be a choke point of feeding the engine. They needed bigger carbs. But the small issue was that Weber didn't make anything larger, and they weren't interested in doing it either. Gay actually flew to Bologna, Italy to sit down with Weber's chief engineer, Franco Bellicardi, in the hopes of talking him into making some 58mm throat carbs. Upon receiving a letter from Bill Gay stating that he was going to come over and have a conversation about these magical new carburetors, Bellicardi wrote back and politely told him to stay home and that they weren't interested. But years before, Bellicardi had come to America, a stranger in a strange land, and Bill Gay had actually helped him navigate Ford and other people he was to meet with. He never forgot this act of kindness, and once Bill Gay got to Italy and was sitting in front of him at the table, Bellicardi had no choice but to agree to produce these special 58mm carburetors, and it was done in a rush. In early dyno testing, the engine made 325 horsepower on gasoline in the small carburetors, matching Colin Chapman's ask to the exact number. On methanol, with the now larger carburetors, it made 340 horsepower. On methanol and Hilborn injection, it made 351 horsepower. Adding 20% nitro and the larger carburetors, it made 363 horsepower. And finally, with the Hilborn injection and 30% nitro, the engine made 380 horsepower. The testing that engineers did on the dyno beyond the use of gasoline was purely to see what teams would likely have to work with in terms of qualifying trim with exotic fuels. It was a common practice at this time in Indianapolis history, especially to tip the can of nitro in qualifying to up horsepower and therefore up speed and performance. Now, the gasoline number was the primary concern for the engineers, and the rest of it was literally just testing the limits of the little engine. At the tail end of the dyno portion of the program, the 58mm Webers arrived, and the engine immediately, after fine-tuning, picked up 20 horsepower on gasoline. When you think about this engine and what went into it at this time in history, it's almost impossible to think it wasn't the best pushrod V8 on the planet in terms of its efficiency, design, and all of it was based around a factory passenger car engine. In late November of 1962, and remember, this project started effectively in June, the engineers installed an engine into an experimental 1962 Ford Galaxy. Now, this car had a fastback roof, and they took it to Daytona International Speedway. And with them were two engines. One engine using 103-octane gasoline and their 58mm Weber carburetors, and the other was Hilborn injected on methanol. The little gas burner pushed this tank of a car to a speed of 146.7 miles per hour, while getting 6.41 miles per gallon on the track. The Hilborn injected engine on methanol, more powerful of course, went 154.8 miles per hour while slurping fuel at the rate of 2.22 miles per gallon. One area that had not been totally investigated yet was exhaust tuning. After Daytona, they went to the wind tunnel. They put the car in the wind tunnel on loaded rollers and put a very short axle ratio in the rear end. They would run the car between 5,200 and 7,000 RPM as if it were driving off the corners of the speedway, kind of trying to understand what the exhaust did in the wind stream. Now, this was important to find out not only what it did aerodynamically, but how the exhaust would work in terms of scavenging from the engine to increase power. They came up with 8 pipes, 2 collectors, and a 180-degree style exhaust with equal-length pipes. It was good for aero, it was good flowing, and it would package well in a race car. In January of 1963, this engine, the Phase 2 motor, was installed in a Cobra and sent to compete at the Daytona Continental Sports Car Race. It was a failure. The issue was the valve train. Even with its increased heft, the stud-style rockers were not capable of doing the job, and the dread was palpable amongst this team of engineers on the project. After a period of design and testing, the stud-style rockers were replaced with shaft rockers using a cast Malibu-style iron rocker arm. With this setup installed, the engine was put on a dyno and thrashed for 43 hours, and it sure seemed to be fixed. After being upgraded in the valve train department, this was now considered the Phase 3 engine. It made 365 horsepower on gasoline at 7,200 RPM peak, and it was late. Dan Gurney and the Lotus test car were at IMS in March of 1963 twiddling their thumbs. Before the engine had cooled to the touch, it was packaged and flown directly to Indianapolis for actual on-track testing. Minus fuel, with the engine installed in the car, the whole package weighed 1,130 pounds. Now, in a very 1960s twist, in the thrash to actually assemble the car, some small parts were missing. Gurney and the team ran to a rental car lot, rented at least 1, maybe 2 Fairlanes, and then brought them to the speedway, robbing them of some knickknacks they needed to get the car into running order and onto the racetrack, bolted together with some spare factory parts from their rental cars. On March 24, 1963, Dan Gurney took the car on its initial shakedown runs at the speedway. Amazingly, in a Ford engineering report filed in January, specifically January 4, 1963, nearly 3 months earlier, it was predicted that the car, in its initial and most unsorted phase, would likely lap the speedway at 150.5 miles per hour average. On the 24th of March, 1963, Dan Gurney went 150.5 miles per hour average around the Indianapolis Motor Speedway. That is astonishing. As news leaked out about the test, it didn't seem to raise many eyebrows. After all, Parnelli Jones had qualified at 150.37 miles per hour the year before on the pole, and that was in 1962. Everybody would improve their stuff, so the fact that the little car with the little engine ran 150, it didn't seem to be much to be worrying about because everybody would be faster than that when they showed up in May. What they didn't know is that this car had then been shipped to Ford's Kingman, Arizona testing facility, and they had set up simulations of running the 2.5-mile Indy course on the massive 5-mile oval in Arizona. Thrashing the engine for hundreds of miles at a time, they had been able to achieve fuel economy of 7.74 miles per gallon. Of course, most of that lending itself to the much smaller envelope of the Lotus car versus the massive Galaxy they ran around Daytona, achieving less than 7 miles per gallon at that point. Now, the team tested both Dunlop and Firestone tires. The Dunlops failed early. The Firestones were a little bit larger, but with some rear gear ratio changes, the car should react well, and should have reacted well with those tires. Carrying 50 gallons of fuel, the mass said they could run the race with 1 fuel stop and perhaps finish the whole 500 miles on one set of Firestone tires, which wasn't necessarily totally unheard of at that time. The drivers who knew how to conserve tires could, at this time in history, finish a race on one set. After the engine had all those hard hours and laps on it, the dyno testing kicked back off. It now made 376 horsepower at 7,200 RPM on gasoline, fully broken in. Phase 3 was completed in April of 1963 with the construction of the race engines to be used in qualifying and during the running of the Indianapolis 500. Now, interestingly, while all this had been going on, engineers had created a secret emergency plan if their little engine didn't have the muster to do the job. Well, they did not have to institute the often whispered about Phase 4 in 1963. They knew they had it in their back pocket if it ever arose. Dan Gurney and Jimmy Clark were announced as the drivers for the Ford Lotus cars at the 1963 Indianapolis 500-mile race. Unsurprisingly, when the cars and the drivers arrived at the Speedway in May, few were happy to see them coming. For starters, in the world of the Speedway, green cars were bad luck, and the Lotus was, especially the one Clark was driving, green. Strike one. Cars with engines behind the drivers were sacrilege. And wait a second, what were those tires? Colin Chapman had designed his car around the use of 15-inch tires. These happened to be Firestones. Racers, team owners, and other mechanics protested their use and encouraged the tires to be banned because no one else had them or seemingly had access to get them. Now, Firestone decided to burn the midnight oil to produce a run of these tires so they could be scored by anybody who wanted them in the pits. Some people wanted them. Many people tried them. They didn't work for anyone else, and as such, they stayed on the Lotus and basically nothing else. During the month of May, Colin Chapman and Jimmy Clark were actually flying back and forth across the ocean, running Indy some weeks to test and then flying across the ocean to run Grand Prix races on the F1 circuit in between. Gurney was testing his car and working with the Ford contingent, mostly at the Speedway. During qualifying, disaster struck when Gurney wrecked his primary race car and went to a backup. Jimmy Clark ended up qualifying in 5th place, which placed him in the center of row 2 with a speed of 149.75. Gurney qualified 12th in his backup car at 149.019 miles per hour, which placed him in the 4th row outside. Almost immediately after the green flag start in 1963, Gurney and Clark were running 1st and 2nd. Parnelli Jones was running 3rd. The Roadsters had more speed on the straights, but the Lotus chassis could virtually run flat out through the corners, pulling ahead in that section of the track. The cars, which are called rear engine but are truly mid-engine, simply turned far, far better than the front-engine Roadsters. Leading on lap 95, Clark came in for a fuel stop, and the Lotus crew botched it horribly. He left 34 seconds behind Parnelli Jones, who he had been sailing away from. The stop was a debacle, but he still had time on his side. With 50 laps to go, Jones was leading by 43 seconds. Gurney, who had more pit trouble on his own, he was now a lap down in 4th place. With 25 laps to go, Clark was pouring it on, now behind Parnelli Jones by only 5 to 6 seconds. Now, he was about to swallow Jones whole, but then there was a big problem, which would turn into one of the great controversies in Indianapolis 500 history. Parnelli Jones' Roadster was leaking oil from its oil tank, and lots of it. Officials were on the verge of black flagging him at this late moment in the race. His team owner went over, created a screaming match on the flag stand with the actual race officials, and no black flag was ever thrown. Sliding in Jones's oil, Clark was forced to fall back in order to prevent from wrecking, finishing 33 seconds back and roundly disgusted. It sure seemed like race officials didn't throw the black flag in order to prevent the foreign invader and his strange car from winning their race. At least it felt that way to Chapman and Clark. They were truly disgusted, but the Ford engineers were kind of elated. No one in their right mind had given them a fighting chance of taking little more than a year to come up with an engine that would compete, let alone one based on a lowly passenger car V8. Their true redemption came the weeks following the 500. At Milwaukee, the Ford Lotus combination completely dominated. In Trenton, New Jersey, they were walking away before mechanical issues stopped them as well. It was proven. So the natural question became, what next? What only a tiny handful of people inside Ford knew is that there actually was a Phase 4 version of the 255 cubic inch V8. Now, that was in clandestine planning in case the Phase 3 engine didn't live up to the power and durability that was needed. Of course, this plan was not executed in 1963, but Ford was now invested, and having run it up with their little pushrod engine, executives gave the green light to proceed with a more advanced plan for the 1964 race, and this started immediately following the 1963 Indy 500. The first question is, why would you change anything? And the answer is embedded right there in the culture of the Indy 500. At this time in history, it was Copycatville, USA. It wasn't just something that they considered, it was something that they knew to their core. Back in '62, when Bill Gay went out checking out the USAC Champ Car Series, he reported back and quoted this: "If A.J. Watson hung a weenie on the side of his car, the next week 10 cars would have a weenie hanging off of them as well." End quote. In a report to the SAE on May 7, 1964, entitled "The Ford Dual Overhead Cam Competition Engine," A.J. Scussel of the Ford Motor Company laid out an incredibly detailed evolution of what would be the next step for the Ford IndyCar V8 program. Using this same mentality, Ford assumed that there would be a massive increase in performance in 1964 with advancements in chassis technology and perhaps even engine technology as well. They figured if they sat still, they'd be left in the dust. They also knew that at 375 horsepower, 360 pound-feet of torque, and 360 pounds, their little pushrod wonder was all but maxed out. So in typical fashion, Ford set 4 clear objectives. Number 1, make the 1964 Fairlane engine as competitive horsepower-wise at the lowest possible feasible RPM. Number 2, hold the weight of the engine to 400 pounds. Number 3, use gasoline fuel, not methanol, for its gas mileage advantages. And number 4, keep carburetors or go with a known and proven fuel injection system. The unstated goal was to reuse as many parts as possible from the 1963 engine, increase the horsepower by 50, and gain even more reliability. Yikes. 8,000 RPM was set as the target feasible RPM. This absolutely removed the possibility of a period-style pushrod engine, especially if the target was to be run for hours at a time. And again, Ford engineers devised a multiple-phase program. Phase 1 was to design, fabricate, evaluate a dual overhead cam engine, and use as many of the 1963 pushrod engine components as was possible. Phase 2 is to have a second series of experimental engines constructed with design changes from Phase 1, test results on combustion chamber design, induction, and multiple ignition points per combustion chamber, get this, using up to 3 spark plugs per cylinder. Phase 3 was to build the final versions of the engine and test them relentlessly up until race day at the Indianapolis 500. The Phase 1 engines of 1964 were built using the same 63 design for the block, the crank, connecting rods, bearings, water pump, oil pan, and gear drive. Now these were tested with overhead camshaft cylinder heads at higher RPM levels. Different fuel systems were tested as well, as was the layout of the engine considered for packaging in different race car chassis. Now what was learned in this early phase was that all the 1963 hard parts were more than capable of doing the work with adjustments. The engine, with a 4-valve cylinder head, dual overhead camshafts, and a pent roof combustion chamber, made 400 horsepower at 8,000 RPM in its raw, nearly untuned form in Phase 1 fashion directly out of the gate. Now, the first initial problem was that the chamber design did not allow enough cooling of the exhaust valves, so that would need to be revised. Also, the ignition was being driven off the back of the camshaft, and the camshafts were deflecting and twisting so much at RPM that spark scatter was a big issue. So they readjusted that, moving the drive to the ignition system to the front of the camshaft, which kept it highly accurate to the cam timing, and everything was fine. Despite reaching out and asking really nicely, Weber flatly refused to be involved in the 1964 version of the engine. They had gone far enough with the 58mm carburetors in 1963 and did not have the resources or want to go down the road of redesigning something even different for this one specialized engine. That means the engineers were going to go with fuel injection, and they chose the Hilborn system with its lower pressure and constant flow setup to feed the motor. One of the most iconic parts of this engine, the fact that the exhaust valve and its port are above the intake port and valve, meaning that the exhaust actually came up toward the center of the engine and the intake basically had a straight shot to the valve itself. Didn't happen because it was initially designed that way. In fact, it was the opposite in the early engines. The issue is that when the engine was first tried to fit in a car, the exhaust had to be run through the suspension. If you look at the layout of the heads, the exhaust would have to come down the outside of a race car chassis. Remember, these are small Indy cars, and it has to go back somewhere. So when they ran the exhaust backward, there was only one way to put it, and that was to run it through suspension pieces, which was strange and awkward and overly complicated. By relocating the position of the exhaust valve and allowing the exhaust to actually rise up over top of the engine, it meant that the exhaust itself could be bundled together and sent straight back out over the top of everything, not interfering with the suspension or the rear of the car in any way. So let's get into some of the more interesting details of the 1964 version of this engine, and for starters, we should talk about the block. Now, Ford used the same pushrod block and even kept the cam tunnel in it for 1964. How did they do that? Well, they took a tube and inserted it where the camshaft would go. The tube worked as a kind of diffuser for oil drain back. It actually helped vent the crankcase as well as keeping oil from pouring down directly onto the crank and being turned into foam as the crank spun around in it. The cylinder heads used 1.46-inch diameter valves, and there were 4 of them per cylinder. The camshaft had 440 lift, 306 degrees duration, and a tight 87 degrees of valve overlap. Amazingly, the cam followers used in this engine were bought straight from Meyer Drake. They were the same ones used in the office. The valve springs used 360 pounds of pressure when open and 95 pounds on the seat when the valve was closed. The cylinder heads and how they were made are among the most advanced pieces in the history of engines at this time. The heads as cast had combustion chambers within 3/16 of an inch of what the final dimensions were to be. Because of their pent roof shape, traditional machining methods of the 60s would be near impossible to get right, so these heads were actually finished via EDM, or electrical discharge machining. This is an advanced process in the modern age, and in 1964, when this work was happening, it was pure science fiction. In fact, in magazine stories of the time, writers were told that it was, quote, a miracle of the modern age, and never actually given the EDM name of the process used. It's very reasonable to say that no other race car on the planet had ever had EDM finished machine cylinder heads, and also it's fair to say that few, if any, have them today. An advanced engineering area of Ford was hailed to do this work, and it went perfectly. The ignition timing was locked at 52 degrees advanced, and after 2,000 RPM, the engine really didn't want any more than that anyway, so that was fine. A device was used to pull the timing back to aid in starting the car when it needed to be fired up. Sticking with the same 12.5-to-1 compression ratio from 1963, the engines would have a raspy idle of about 2,000 RPM. The connecting rods were slightly modified again for strength. A larger wrist pin was used, and more material was added on the big end for the increased RPM, but otherwise they were factory forged-style rods, nothing really exotic. The crank and rod bearings were upgraded in this engine, as the ones used in the 63 version didn't like the higher-spun 1964 model. The same style of gear drive used in the 63 engine was used here, but it was more complex. There were 14 steel spur gears with straight-cut teeth, and the cam timing could be adjusted in this system as well. The Phase 2 engines were built and tested to refine their ignition, cylinder heads, and fuel systems. And some were built with up to 3 spark plugs per cylinder head and tested that way. There was a minimal amount of power gained on the dyno, but a massive amount of complexity, and because of that, 1 spark plug per cylinder was simply settled on. I can only imagine what these things actually looked like with that tangle of wires going around all of this stuff. The Hillborn injection was a continuous 60 psi flow at 8,000 RPM, and as the small engine only needed 245 pounds of fuel per hour, that was plenty. Lots of testing was done on the fuel injection in the wind tunnel, which could generate different heat scenarios as well as winds up to 120 miles per hour. Vapor locking was actually a concern initially, but it was never found to be a problem in all of this testing. The oil system was again a dry sump like 1963. The pump size was increased by 100% with a 50% larger pickup tube. Now, early versions of this engine had windage issues and would start throwing oil out of the breathers at 8,000 RPM. Engineers simply increased the size of the scavenge pump and it cured the problem. It also increased oil control in the bottom of the engine. Lastly, there is the exhausts. Now, maybe one of the most visually incredible parts of this engine. A multitude of systems were tested until the final setup of 71.6-inch pipes were settled upon. The 71.6-inch pipes were ideal, but 36-inch and 18-inch systems were developed for other chassis packages. The final 180-degree style bundle of snakes with a pair of collectors reportedly increased throttle response off of idle due to the better scavenging properties it had for exhaust gases. SAE 50-weight oil was used throughout the testing and the operation of the engines, and the fuel used was 102.9-octane gasoline. The final weight of this Phase 2 engine was 406 pounds. That is within 6 pounds of the initial goal of 400, and it would just have to be good enough. So what kind of power did the finished product make? The Phase 3 engine, properly tuned, made 425 horsepower at 8,000 RPM on gasoline, with 295 foot-pounds of torque at 6,400 RPM. On methanol, the engine made 475 horsepower at 8,000 RPM. Moving rapidly into Phase 3 in the race engines themselves, Ford engineers were cranking along quickly. As the basic long block program was the same as 1963, completing multiple engines in this phase was a less taxing but still challenging part of the program. By October of 1963, the Phase 2 engine was in a chassis and being run. It was first run at Indianapolis October 28th through the 31st. Now, this was a basic shakedown for proof of concept. Early issues were identified with the engine, the fuel injection was sorted out, and this is where the oil slinging was first identified and needed to be fixed. January 20th to the 27th, 1964, Bobby Marshman tested this car at Kingman, Arizona at the Ford facility, and he had 190 miles an hour with the first Phase 3 engine in his race car. All the Indy and dyno issues were corrected. Different exhaust systems were also tested in this phase. In February of 64, there was durability testing for basically the entire month in Arizona. In March of 64, the whole team went back to Indianapolis. Phase 3 engines in chassis that would be raced were now tested on the Speedway. Making laps and fine-tuning the performance of the whole package, a best speed achieved was 153.8, and the unit was achieving 183 miles per hour on the straights, accelerating from 6,300 RPM out of the corner to 8,000 RPM before entering the next. The cars would accelerate 6,300 RPM to 7,000 RPM in the short chutes between corners. Now, this was a single-car test with no traffic or other factors, but the numbers were very promising. The engines were ready to do battle, it seemed. In April of 1964, they went back to Arizona for final fuel injection testing, maintenance, and wear testing. May came, and the sun was shining on Ford. 7 entries were running the dual overhead cam engine in the 1964 Indy 500. They would be Eddie Sachs, Dave McDonald, Eddie Johnson, Bobby Marshman, Jim Clark, Dan Gurney, and Roger Ward. 4 different chassis types were used among the 7 racers. Sachs was in a Hallebrand. There were the 2 Lotus cars. There was Dave McDonald in a Mickey Thompson chassis, and a Watson chassis being used by Roger Ward. Now, how did these 7 teams get the available engines? For Clark and Gurney, that was easy. They were in the program. Mickey Thompson had very close ties to Ford, so that tracks as well. Bobby Marshman was a test driver for the program. He got an engine to use for his team. Remember, A.J. Watson let Ford into his chassis shop to learn, so he was in as well. And I'm guessing Hallebrand aided Ford in their use of magnesium for the engine project, so he also had a close connection. Effectively, anybody that got an engine somehow participated in Ford's development of said engine. The 1964 Indy 500 was, in large part, a disaster in the both human and mechanical scale. This, of course, the infamous race that ended the lives of Eddie Sachs and Dave McDonald in an early lap crash, stopping the event for more than an hour while the disaster was tended to, but eventually, things actually did start again. When they did start again, Jimmy Clark and Bobby Marshman rocketed out front and the route was on. Until it wasn't. Colin Chapman had insisted on running Dunlop tires, and after leading the first 14 laps with ease and seemingly on cruise control, one of Clark's rear tires failed at speed, ruining the rear suspension of his car on lap 47. He was done, and luckily not hurt in a wreck. Gurney was the next to suffer a tire failure, and after that the car was withdrawn for simple safety concerns. It was just too dangerous. No worries, Bobby Marshman was running like lightning, and was actually getting close to lapping A.J. Foyt. He was leading the race by 90 seconds. Lapping Foyt was something Marshman really didn't have to do, but he kind of seemingly became obsessed with the idea. Somehow, he managed to dip the car too low in the apron of the racetrack, bottoming the thing out, and in doing that, he ripped the transmission plug out of the bottom of the transmission, evacuating its contents onto the racetrack, bringing the black flag out, and retiring him from competition. This, of course, left Roger Ward as the remaining hope, and after botched pit stops, he, despite his best efforts, finished second, 1 minute, 24.35 seconds behind A.J. Foyt in his old-school Offie-powered Roadster. A.J. Foyt reveled in this moment, talking about his antique little car, celebrating his victory, and rubbing Ford's nose in it. One of the most surreal photos in Indy 500 history is the one of A.J. Foyt holding the newspaper, proclaiming the loss of Saxon McDonald while also celebrating his win on the front page. As one might expect, the end result here did not go over well at Ford. In fact, Lee Iacocca flipped out and demanded a full investigation into the failure and effectively demanded that Chapman be fired for his insistence on the Dunlop tires, which completely sunk the factory-back cars. Jimmy Clark swore the race off and said he'd never go back again. Now, somehow Chapman was able to keep his job. In fact, he was able to use a contract clause to keep the cars from being taken away from him, and he actually ran them at ensuing USAC races in '64. Now, A.J. Foyt continued to dominate the season, but the Ford-Lotus combo was fully shaken down, and eventually cooler heads prevailed. Some Ford executives flew to England, made Chapman a 1965 offer that cut his budget and his powers significantly, told him that the offer was contingent on Jimmy Clark coming back, and basically told him to figure it out. Now, Chapman initially refused, but then he gave in, took the offer, and he sweet-talked Jimmy Clark into one last run at the 1965 Indianapolis 500. By 1965, the Ford dual-overhead cam program had turned into an actual race engine business. Louis Meyer, yes, of the Meyer-Drake-Offenhauser engine fame, was actually hired by Ford to be their sole agent in the sales and service of these engines. Meyer sold his half of the business to Drake and went all in with Ford. Now, Meyer opened up a shop in Indianapolis in the shadow of the Speedway. Ford was taking a loss on every engine at this time. The computed price was $31,400 per unit. Meyer would get them for $15,000 apiece and sell them for $22,800, making a seemingly good profit. Offenhauser engines at this time were $12,000 apiece. It should be noted that Ford provided Meyer all the parts and he would assemble the engines in that Indianapolis shop. There were 68 entries into the 1965 Indy 500. 45 of them had their engines in the back, and 24 of them had Ford power. This presented an unplanned issue. At this time, most Indianapolis mechanics had no idea how to work on an engine as intricate, as compared to an Offie, as the Ford dual overhead cam V8. Chapman's Lotus mechanics literally took chisels to the block to make the engine fit their car. Upon seeing this, Ford forbid anybody from his team from touching the engine and made it their sole business to tune those race cars. Oiling issues also became a problem. Now, engineers had used a very fine, small filter on the engine, but as the service was done in the grungy garage areas of the Speedway, specks of dirt, grease, and other matter would get into the filter and clog it very quickly. George Sallow, one of the great IndyCar mechanics of all time, adapted a large oil filter from an aircraft engine to work, and this was made factory protocol by Ford. Qualifying for the 1965 race was electrifying. A young rookie named Mario Andretti set a qualifying record at 159.849 miles per hour. As he was being feted and interviewed after the fact, Jimmy Clark got in his car and then shattered it with a 160.729 mile per hour average, the first to average over 160 at the Speedway. As he was smiling, A.J. Foyt, again using Ford power, went out and busted that record to 161.235 lap average speed. It was a crazy sequence, and it was all powered by Ford. While the engine had not changed from 1964, Ford's approach certainly did. When qualifying was done, 18 of the Fords were in the field. All 18 engines were rush-flown back to Dearborn, where they were sent to a factory to be stripped, inspected, and dyno-tested before being flown back. They sent the engines not to race engineering specialists, but to a group of experienced assembly line people who were typically building and doing QC work on truck engines. The men who got put on this special assignment treated it as if it were their life's destiny to win the Indy 500 themselves, and the engines are all perfectly torn down, reassembled, and done in a manner as well as any master mechanic in the world could have done. A band of truly unsung regular Joe heroes wrenching their hearts out. The race was total domination by Ford. 11 cars were running at the end, and 8 were Ford-powered. Jimmy Clark didn't just win, he was coronated. Leading 190 of 200 laps, the only time Clark trailed was when he came in for his first pit stop, and A.J. Foyt stayed out. Now, famously, that pit stop was executed by the NASCAR Racing Wood brothers in less than 20 seconds. They were brought in to replace the hapless Lotus crew from 1964. The second mandatory stop was barely over 20 seconds. Their work dumbfounded every other team on pit road. Clark became the first foreign driver to win the Indianapolis 500 since 1920 when Gaston Chevrolet did the job. Clark led from lap 1 through 65 and then laps 75 through 200. Amazing. Of the nearly 20 Ford engines that started, only 3 failed, and all 3 of those run a stiff load of nitromethane. The other Ford-powered cars that dropped from the race were for reasons like transaxle and clutch failure. One car lost a wheel. Dan Gurney's car actually had a gear train failure in the front of the engine. Now, the engine would go on to dominate the rest of the season as well, especially on the mile-long tracks USAC ran a lot of their season on. In basically 2 years, Ford had entered a race in a racing series with a beefed-up passenger car engine, evolved it into one of the coolest and winningest V8s of all time, and captured a market that had been dominated by Offie for decades. The Ford dual-overhead cam engine would win the Indy 500 in 1965, 66, 67, 69, 70, 71, and lastly in 1977. Incidentally, the engines were then branded Foyt V8s as Ford basically turned the entire program over to A.J. Foyt in the early 70s. Drag racer Jim Busby famously placed 2 of them in a dragster chassis, raced the car at a single NHRA national event, collected a trophy for Best Engineered at the meet, and then sold the engines back to an IndyCar team for a tidy profit. I've told the story of one of these engines being run at the Bonneville Salt Flats in a Mustang on this very channel. Well, this part of the story comes to a close. There's another chapter here, and that one's coming soon. See, the Offenhauser engine wasn't dead. Not by a long shot. And the devotees of it had already begun working on ways to make their favorite four-banger meaner, faster, and stronger. And while Ford was laughing now in this moment, on the horizon, the distant horizon, the Indy horsepower war was set to take a tremendous leap forward. And that antique racing engine, first made by Harry Miller in the 1920s, had way more life in it than anybody expected. The Offie deserves its proper history told on this channel, and it will be. Not only that, we'll find out how it came back and punched Ford straight in the mouth. Stay tuned. I'm Brian Loans. Thanks for watching. Like and subscribe for racing history, automotive history, and stories that'll engage your brain and maybe even move your soul.